I hope you had. I hope you all had a good weekend. Wait a minute, that I have to stop the streaming in my. So today we are going to have a lecture and so on, and after in the later afternoon we are going to have also a keynote lecture. So we're going to have 3 keynote lectures this week. So this morning we start with Dr. Yuri TIMROV from the, let's say, long-term friend of the Quantum Espresso package, talking about the time-dependent density functional perturbation theory. We'll try to collect questions from the streaming. So everybody that is following the streaming, please feel free to make questions on the chat. While here on Zoom, I mean, as usual, we wait at the end of the lecture, and then with the reaction, we can leave also participant interacting with Yuri at the end of the talk. So Yuri, stage is yours. Good luck.
Thank you, Ivan, for the introduction. Hello to everybody. Okay, just give me a second. Okay. Okay, so today we're going to discuss about time-dependent density functional perturbation theory. I hope you enjoyed the first week of Quantum Espresso school, and I hope you will enjoy also the second week, and it will be as successful as the first week. Okay, to get started, let me remind why we are here. So we are here to learn the Quantum Espresso package. I would like to share with you this data, which is the number of citations of the 2 main Quantum Espresso papers shown below, published in 2009 and 2017. So you can see that the citation of Quantum Espresso is really increasing every year. And in particular, in 2020, we have essentially that every day Quantum Espresso is cited in 10 papers. So for example, today, 10 papers will cite Quantum Espresso. This gives us idea of really that the fact that Quantum Espresso is a widely used electronic structure software. As you learned last week, Quantum Espresso is a suite of codes, open source codes for electronic structure calculations and materials modeling at the nanoscale. It is based on density functional theory, plane waves, and pseudopotentials. And as I already mentioned before, this is the most widely used open source software for electronic structure calculations in materials. On this figure on the left, this is a schema that describes the nature of Quantum Espresso package. There are different layers. For example, the highest layer, it's so-called property calculators. There are different codes, for example, the PW code that you learned during the first day of last week to solve the Conchem equation and to obtain the ground state of your system. There is also another code called CP for Carr-Parinello molecular dynamics. You will learn it this week on Wednesday. Last week, you learned about Nugget elastic band with Tone, Pietro, and others. There is another code called PW cont for transport. There is a bunch of post-processing codes collected in the repository called PP and many others. More advanced codes in Quantum Espresso are phonon that we learned on Friday to compute phonon dispersions. Today we will learn TD-DFPT for spectroscopies like optical absorption, electron energy loss, and magnetic excitations. There is also GWW code, which is, as you can guess, the GW method. EPW code to compute electron-phonon interactions. Also, last week, we discussed briefly about the HP code for computing Hubbard parameters and many, many more. And lower layers are more technical, which we are not going to discuss during this school. This is how the package is organized in terms of libraries and modules. Okay, so as I said, today we will focus on TD-DFPT. So what is this and why do we want to discuss TDD-FPT? So maybe you've heard such a term as computational spectroscopy. So the idea is to go from the ground state to the excited state. So last week, as I said, we learned how to solve quantum equations, to obtain the ground state of the system, how to compute band structures, shown here for some material, projected density of states, and many other fundamental properties of materials. But now we want to go further, and we want also to study materials in their excited state, because there are many things, we can do many things with just ground state DFT, but we can do many more things if we go further to the time-dependent, to describe time-dependent phenomena. So this is the band structure. On the y-axis, we have energy in electron volts, and the x-axis are the high symmetry directions in the Brillouin zone. And L, gamma, X, UK, and gamma are the names of high symmetry points in the Brillouin zone. And this spaghetti are electronic bands. So what we can see here, we have the band gap. This is the energy separating top of the valence bands and the bottom of the conduction bands. So this is, let's say we have our system, our material in the ground state, and then all of a sudden we irradiate our material, for example, with light. So we send photons to our materials. What happens is that valence electrons, they absorb photons and make transitions from the valence band to the conduction bands, shown with these red dashed arrows. So these transitions occur when the energy separation between valence and conduction bands equals to the energy of the photon. So when there is a resonance. So there are different transitions. So to describe this, of course, we can say we can use just standard DFT. We know energy of valence bands, we know the energy of conduction bands, we just take the energy differences and that's it. Well, this would be the simplest approximation, of course. And as we will see in the rest of my talk, this is not satisfactory when you want to make a comparison with experimental spectra. So we need to do more advanced simulations. So to do that, we need to go to the time domain. So because so far it was all static, we didn't have time, it was all fixed in time, but now we need to introduce a time variable and extend DFT to the time domain. So this will be the topic of today. This is the outline of the morning lecture. First, we will discuss the basics of time-dependent density functional theory, in particular two Runge-Gross theorems. Then we will discuss linear response TDD-FT, or it's also called TDD-FPT, where letter P stands for perturbation. I will explain later why we have this acronym. And we will discuss four methods, namely Dyson method, Steinheimer, Liouville-Lanczos, and Cassida-Davidson. And in the second part of my talk, we will discuss applications of TDD-FT to describe optical absorption spectroscopy, electron energy loss, and inelastic neutron scattering, which is for magnetic systems. All right. So let's start with time-dependent Schrödinger equation. I hope I explained why do we need to go to the time domain. So as it's written on the slide, like in the static case, we want to use a Born-Oppenheimer approximation, which tells us that electrons move in the field of clumped nuclei. So the mass of nuclei is much larger than the mass of electrons, so we can assume that nuclei are fixed and electrons move around of nuclei. And the evolution of the non-relativistic interacting many electron system is governed by the so-called time-dependent Schrödinger equation written on this slide. Last week we discussed time-independent Schrödinger equation. Now we go to the time-dependent extension. So in the first equation, we see that there is a wave function capital psi, which is the many-body electronic wave function. It depends not only on the position of all electrons labeled by Ri, but also it depends on time. There is also the operator H with a hat, which is the quantum mechanical Hamiltonian. It also depends on electronic positions and on time. And the expression for this Hamiltonian is written on the second line. We have the kinetic term, as usual. The second term is the electron-electron interaction term. And the third term is the external potential. And notice that the external potential depends on time. Because when we, for example, irradiate material with light, so this is not a static external perturbation, it is time dependent. So this is why we have time in external potential. And the solution of the time dependent Schrödinger equation for the main electron system is even more complex than the solution of the static or time independent Schrödinger equation. As in the case of static theory, we want to go from wave function, which is a very complicated object, to charge density, which is much more convenient. So by the analogy to the static case, we go from the wave function, which depends on 3n plus 1 variables, where we have 3n special coordinates and 1 time coordinate. So 3n plus 1 in total. So instead, we use just the charge density, which is a function of only 4 variables. So 3 special coordinates labeled by vector r, which is x, y, and z, and 1 time coordinate. And the charge density, time-dependent charge density, is given by this expression, where we have capital N, the number of particles, electrons, times the integral of the square modulus of our many-body wave function, integrated over all special coordinates except 1, r. So this is the density in a specific point in space at a specific moment in time. So this is really the basic object for us. And in 1984, there was this breakthrough paper in Physical Review Letters by Runge and Gross entitled Density Functional Theory for Time-Dependent Systems. So this is when TD-DFT was introduced. Again, just to make an analogy with DFT, as you remember from last week, in DFT, we discussed about one-to-one mapping between static charge density and static external potential using minimization principle of the total energy. But now we are talking about TD-DFT, and we want to do something similar, and we will see how to do that. So we want to make a straightforward extension of this same idea to the time-dependent domain. But this is not that easy, actually. There are issues because the total energy is no longer a conserved quantity. So in time, total energy changes. And this brings us to the first Runge-Gross theorem, and its exact statement is written here. Let me read it. So the first theorem tells us that for any system of interacting particles in an external time-dependent potential V external R of t, which can be expanded in Taylor series with respect to time, and given an initial state, psi 0 of R, there is a one-to-one correspondence between time-dependent external potential and the time-dependent density N of R and T, apart from a trivial function of time. So this theorem tells us that, like in a static case where we said that there is one-to-one correspondence between potential and the density, both are static, also in the time-dependent extension case, we have the same one-to-one mapping between external potential and the density, but now they are dependent on time. So this is really important. So therefore, all observables can be regarded as functions of the time-dependent charge density. While in the static case, all observables were regarded as functions of static charge density. So, but in contrast to the DFT, in TD DFT, we need to set initial condition, of course, because the system follows an evolution in time, and we need to know the starting point. So this is in the theorem, this is corresponds to psi 0 of R at the initial moment T0. So as I already mentioned briefly before, in TD DFT, the variational principle cannot be formulated in terms of the energy, because total energy changes in time. And alternatively, there exists a quantity which is analogous to the energy. This is so-called the quantum mechanical action functional. And this brings us to the theorem 2. Theorem 2 tells us that the quantum mechanical action functional, which we call A, which depends on n, and notice the square bracket. So this is to note a functional. It's not a function. Function, if it was a function, it would be round brackets. But to denote functional, we use a square bracket. So for a quantum mechanical action functional A, defined this way, which is the integral in time from some starting moment in time t0 to some time t1 of this expectation value of this operator I h bar partial derivative over time minus the time dependent Hamiltonian, and the expectation value on the time dependent wave function, so becomes stationary at the exact time dependent density n0 of R and T, which corresponds to the external potential V external of R and T, given the initial state psi 0 at time t0. So stationary, it means that the functional derivative of the expectation, of the action functional with respect to the time dependent density evaluated at the n0 equals 0. So a few comments about this theorem. So theorem 2 means that it is possible to solve the time-dependent problem by searching for the stationary point of the action A. And in contrast to energy in the static case, the stationary point is not necessarily a minimum. It can be also a maximum. So what matters is that it's extremum, so that its functional derivative is 0, but can be minimum or maximum. And the value of the action itself does not provide any relevant additional information because the action evaluated at density n0 is 0. So it's not really something meaningful for us. Okay. Now let's discuss a bit more about this quantum mechanical action functional. So in TD-DFT, the action functional A can be decomposed on components like in a static case. So if you remember last week, we brought the functional as a sum of several terms. Here it's very similar thing. We have the kinetic term, Hartree term, exchange correlation term. And if you remember, I don't remember if it was mentioned last week or not, but in standard DFT, the exchange correlation term was called the stupidity energy by Feynman, because this is, we bring in that term all that we don't know. So that's why it was called stupidity energy. So we have the same sort of term in this case. And the last term depends on the external potential. And notice that potential depends on time and density depends on time. This was discussed before. In particular, the Hartree term, action term, has this expression. You may notice that it looks very similar to the static case because we have this double integral over special coordinates, n times n divided r minus r prime, but now they are dependent on time. And moreover, there is another integral over time from t0 to t1. And in order to approximate the unknown action functional A, Gross and Kohn have introduced an auxiliary fictitious system of non-interacting particles that satisfy these time-dependent quantum equations. Again, in analogy with the static case of last week, Kohn and Shem introduced the auxiliary system of non-interacting electrons moving in the effective potential, and the density of this system, auxiliary system, was equal to the density of the true interacting system. So here in the time-dependent case, it's exactly the same idea, but just generalized to the time-dependent case. So now Gross and Kohn the same. Okay, let's try to do something similar. Let's introduce an auxiliary system, now time-dependent, but non-interacting. And the density, the time-dependent density of this auxiliary system must be equal to the density of the true interacting system. And this was described in this next second fundamental paper. And this brings us to the time-dependent quantum equation. It's written here. We have on the left-hand side the time derivative of our one electron quantum wave function, which depends on spatial coordinate and time. And this equals to the this operator acting on the same one electron wave function. The operator is nothing but the kinetic term plus the effective quantum potential, but now this effective potential depends on time. And those non-interacting electrons are moving in this effective time-dependent quantum potential. This time-dependent quantum potential, again, can be decomposed on three parts: the Hartree term, exchange correlation term, and the external potential. And each of them is written below. The Hartree term looks like in the static case, but now it depends on time. The exchange correlation term is defined as the functional derivative of the action, exchange correlation part, with respect to time-dependent density, and plus the external potential that we apply to the system. And the density is defined in this way, which is the sum over I. I labels our particles, electrons, which are n, and the square modulus of the one electron time-dependent quantum wave functions. So actually, there is not that anything difficult. It's really, if you learned very well the static case, the standard time-independent DFT, so it's quite easy to understand each term here in the time-dependent extension. Okay, and now we need to solve somehow the problem of the time-dependent exchange correlation potential. So we had to do something in the static case. We had to use some approximations like LDA, local density approximation, or GGA, generalized gradient approximation. So we need to do something similar here in the time-dependent extension. And the easiest would be to use so-called adiabatic local density approximation called ALDA, which is obtained by evaluating the standard LDA potential at the time-dependent density n of R and T. It's written mathematically here. So again, I recall that square bracket, it means a functional. So V is a function of the density, and also, at the same time, it's also the function of the position and time. So it's quite complicated object. So we put in this object density, which is a function by itself, and depending on the value of the function, this expression obtains some specific value. But now we want to approximate this complex object, and we say that the exchange correlation potential is actually a function of the density that depends on R and T. So this is a drastic approximation, because strictly speaking, this potential should depend on the density at all previous times, not only at this specific moment in time, but also in it needs to know the history, what was before, how did it behave in the past, this density. But we make really a quite strong approximation, saying that we just want that this potential depends on the density at this very moment. Of course, there are limitations of this approximation, such as we cannot describe double excitations, charge transfer excitations, and other things. Okay, so that was the basics. We discussed time-dependent Schrödinger equation, two Runge-Gross theorems. Now we need to solve somehow this time-dependent quantum equation. And there are different methods. In the following, we will discuss 4 of them. Okay, so we have TDDFT, and we can now define 2 cases, 2 regimes. One is so-called linear response regime, and the second is the non-linear response regime. So in the linear response regime, we apply the external perturbation, which is weak. This would allow us to use the perturbation theory, expand all quantities in Taylor series, and cut the expansion, for example, at first order. And this would give us the linear response because we cut at the first order, the expansion. And these equations can be solved either in time domain or in frequency domain. But the majority of cases are done in a frequency domain. I will discuss in a moment. And second, there is nonlinear regime when the external perturbation is strong. This is, for example, useful to describe ultra-fast physics. And TDDFT equations are solved in the time domain. We will not discuss today non-linear response regime. We will focus on the linear response case. Okay, so this is called in the literature linear response TDDFT, or there is acronym TDDFPT. I will discuss in a moment why this second acronym. So let us assume that the time-dependent external potential is weak, and it can be written in this form. So our external potential is written as a sum of the static potential. So it doesn't depend on time. This is fixed in time. Plus a second term, we label it with V prime, which depends on time. So this is our starting point. Given this expression, the density can be expanded in Taylor series. So we write our density as the 0 order term, which is time independent, plus the first order term n prime, depending on time, plus the n double prime, etc. We can continue the expansion till infinity, but of course we don't want to do that. We want just to keep the simplest case, just the ground state case plus the linear, the first order term. And we, starting from the second order term and higher order terms, we neglect them. So this is an approximation. This being said, we can write this object n prime, which depends on time, as a function of the external potential V prime external. And the connection between these two objects, the external perturbing potential and the induced time-dependent density, so this link is via the function chi, which is the so-called susceptibility of the material. So this function chi depends on special coordinates r and r prime, so it's non-local, and it depends on times t and t prime, but actually the difference of time. And we have integral over r and over time. Time-dependent density functional perturbation theory is TDDFT in conjunction with perturbation theory. So we'll add this letter P because we use perturbation theory. As you can see, we expand in Taylor series, we cut at the first order. So since it's first order, it's called linear response. It's linear. There are no non-linear effects. So this is why And also last Friday, we discussed about DFPT. It was the static density functional perturbation theory. But now we add a prefix TD, which is time-dependent extensions. So in the following, you will see that to solve these equations, we use all those advanced techniques which you learned last week when we discussed about phonons. So that's why we use this acronym TD-DFPT. But commonly in the literature, people also use name linear response TD-DFT. Okay, as I said before, we have at least 4 ways how to solve these equations, linearized time-dependent equations. And let's discuss briefly each of them so that you have an overview of what is used in the community. By the way, TD-DFPT is used in the physics community, but also in quantum chemistry community, in material science. So it's a very popular method. And each community has preferences to this or that method. Okay, let's start with the Dyson method. So we define the charge density susceptibility chi as delta n depending on RT with respect to delta V external at another position R prime, another moment in time T prime. And this object is evaluated at the value of the external potential which equals to V0 external R prime. So this is the definition of the charge density susceptibility. Now, let us use the chain rule for the functional derivatives. I hope you are familiar with the chain rule when evaluating derivatives. Essentially, what we want to do is to say that this object delta n over delta V external can be written as delta n over delta V conchem, delta V conchem, delta V external. So we see we introduced derivative with respect to the conchem potential. But this object is exactly the same as written on the first line. And of course, we have integral over space and time. Okay, and we will use in the following the chain rule again. Now, let's take this object highlighted in yellow, and we can further do some mathematical operations with this expression. So delta V conchem over the delta V external can be written this way because, as we know, the conchem potential is the sum of the Hartree, exchange correlation, and external potential. So basically, this object is nothing but 3 derivatives. The derivative of the Hartree with respect to the external, exchange correlation with respect to the external, and external with respect to external, which gives us simply the delta function. And next, the derivative of the Hartree part can be further written using the chain rule. So we write delta V Hartree with respect to the density and density with respect to the external potential. But what we obtain now is very interesting because, not yet, sorry, just wait a moment. So one more comment that delta V Hartree with respect to the density, we know the expression for the Hartree potential that it depends on the density, so we can evaluate this derivative, and it's simply charge to the power of 2 over Coulomb potential and delta function for time. Okay, we can do the similar thing with the exchange correlation part. We can now use the chain rule, which will give us derivative of the exchange correlation potential with respect to density and derivative of the density with respect to the external potential. And we call this object delta V exchange correlation with respect to the density as Fxc, which is the so-called exchange correlation kernel. And the interesting part that I wanted to say 1 minute ago is this one. It's highlighted in brown that notice that the object that we want to evaluate, the function chi susceptibility, depends on itself, because this is also chi. So we want to find something unknown, and this unknown depends on itself. So how to do that? How to solve this? This is what we have. This is the so-called Dyson-like equation, because susceptibility chi equals chi naught plus some complicated object, which depends on chi, which we want to compute. So this is an equation where unknown depends on itself. And in this integral expression, we have the Coulomb part plus the exchange correlation part. The object which is appeared here, chi naught, is the so-called independent particle polarizability, which depends on R prime and frequency. By the way, here we did the Fourier transform. It's written on the slides. We went from time domain to the frequency domain, because it's more convenient to solve this equation in frequency domain. And this object, it can be shown mathematically how to obtain it. But essentially, it has this expression. We have summation over indices I and j. They label valence and conduction bands. It depends on functions f, I, and j, which are Conchem occupations. It depends on one particle, one electron Conchem wave functions, static ones, divided by h bar omega, which is the energy of the incoming photon, minus the energy difference between conduction and valence bands, plus I eta. Eta is the infinitesimal number, just to regularize the problem. So this function has peaks when the denominator is 0. So when the energy difference between the valence band and conduction bands equals exactly to the energy of the incoming photon, so we have 0 in the denominator, and something divided by 0 gives us infinity. Of course, numerically we cannot deal with infinities, divisions by 0. So to regularize this problem, we add this infinitesimal smearing. Typically, it's Lorentzian. And this object chi naught describes the independent particle excitations. This is what I discussed at the very beginning of today's lecture, when we just solved DFT equations. We obtain valence and conduction bands, and we simply say there are transitions from valence to conduction. But we need to go further, and we need to solve this complicated Dyson-like equation, which takes into account also electronic interactions via the Coulomb interaction and exchange correlation quantum mechanical effects. Also note that it is convenient to go from R space, the real space, which depends on R and R prime, to the G space, to reciprocal space. So we go from R prime in real space to reciprocal space where we have G and G prime. And the connection, we do Fourier transform, and the connection between two objects is via this equation, where omega is the volume, and we have summation over Q points in the Brillouin zone, and G prime are reciprocal lattice vectors. And we have these phase factors here. Okay, so using this Fourier transformation, we can rewrite the Dyson equation in the reciprocal space, and this is how it looks like. So notice that this is not integral equation, it's a matrix equation. It's a matrix with respect to G and G prime, which are vectors. And this equation is solved in practice by fixing Q and at the fixed frequency omega. So Q and omega are fixed. And for fixed Q and omega, we need to solve the matrix of size GG prime. Okay, and the expressions for the Coulomb potential VG of Q written here. And the exchange correlation part, V exchange correlation GG prime, is the Fourier transform of the exchange correlation kernel in real space. Notice that there is, in the literature, you will find that sometimes TD-DFT equations are solved in the RPA approximation. So RPA stands for random phase approximation, which means that we set the exchange correlation kernel to be 0. So we remove exchange correlation and we keep only the Coulomb electronic interaction. And this is called RPA. Okay, I highlight the unknown function, and chi-naught can be computed quite simply on top of the DFT ground state calculation. So from DFT, you know ground state wave functions, phi naught, and you know Kohn-Sham energies, epsilon. So you know everything to compute chi-naught once you solve DFT equations. And then solving Dyson-like equation means you solve TD-DFT equation in the frequency domain. A few comments. There are summations over numerous empty states n prime in the calculation of chi-naught. So in expression of chi-naught, we have sum over k points, but also we have summation over bands n and prime. So n label valence bands or occupied bands, and n prime label empty bands or unoccupied. So in principle, we have infinite number of empty states. But of course, in practice, we cannot have infinite summations. We need to do some cut at some point. And in practice, we need to make convergence tests with respect to the number of empty states. But this is computationally expensive. And this is the drawback of this method. Second drawback is that there are multiplications and inversions of large matrices because, as I said, we have matrices of size G prime, and in practice, the size of this matrix can be easily several hundreds and probably even higher than 1,000. So numerically, this is quite expensive computationally to solve this equation. And finally, the matrices chi-naught and chi of G prime must be computed for every value of frequency. As I said, Q and omega are fixed. So you need to solve this equation for every value of Q and omega. So in optical absorption, Q is 0. So you have only frequency, but still you need to solve this equation multiple times for each value of the frequency. And this is again not practical. This is computationally expensive. This method is not, this is very traditional and conventional method in the community. But due to these drawbacks, we don't really use it. It's not available in Quantum ESPRESSO because there are more advanced methods that I will discuss in the following. But if you are interested in this method, it's implemented, for example, in the Yambo code, which can be used on top of Quantum ESPRESSO. But there are many other codes, like DP code and many others. Okay, now let us discuss about the second method, which is called Steinheimer method. Okay, the Steinheimer method is the following. We write the time-dependent Kohn-Sham equation, I h bar d phi over dt, Kohn-Sham Hamiltonian acting on phi. So we saw this before. I just write, instead of individual terms, compact notation, I introduced the Kohn-Sham Hamiltonian. And this Kohn-Sham Hamiltonian has three parts: kinetic term, external potential, and exchange in correlation potential. The second and the third potentials terms depend on time. Okay, so we have this equation. How can we solve this? So as before, we're in a linear response regime. So we write our external potential as the sum of the ground state potential plus the linear order potential, the perturbation potential, V prime of external, depending on time. As I said before, this being said, we can also write the time-dependent density as the sum of the ground state density and 0 plus the response term and prime, which depends on time. For the same reason, we can also write the exchange correlation potential as the sum of the ground state potential plus the first order term, the response term, which depends on time. Okay, again, we do some, use some notation. We write that Conchem potential is the sum of H naught, which is the ground state Hamiltonian, plus V prime RT, which is the time-dependent response potential. This is the same as written on the previous slide, by just introducing these notations, H naught and V prime. Next, we say that the time-dependent Conchem wave function can be written the following way. So our time-dependent one electron Conchem orbital is defined as the sum of the ground state Conchem orbital plus the time-dependent response orbital phi prime of t, and all this multiplied by this phase factor, where we have imaginary number epsilon v, which is the Conchem energy of the valence band or occupied band, times t and divided by h bar. So this is how we write our total wave function. And with this at hand, by doing very simple mathematical operations, we plug in the definition of this wave function in the time-dependent Conchem equation on the previous slide here. So we put phi in here and in here, and also we put expression for the Hamiltonian. And it can be shown quite easily that we obtain these equations. There are two equations. The first one is the resonant, and the second one is the anti-resonant. So we see that in the second equation, we have complex conjugate star here and here. And we have, since it's we have imaginary number, there is also I changes to minus I. All right, so now we can solve these equations. How to do that? We do the Fourier transform from the time domain to the frequency domain, and we obtain these two equations. So this looks quite complicated. You need to spend some time just to think at each term and the meaning of these equations. But to make a few comments with respect to what you saw last week, you might recognize that these equations look quite similar to the equations shown by Professor Baroni for the static DFPT, density function perturbation theory for phonons. So if we set frequency to 0, so with h bar omega becomes 0 here and here, and also potentials V prime exchange, Hart exchange correlation also, let's say they do not depend on frequency here and here, and we can bring these terms in the middle, PC, V prime, phi naught on the right, and write it as a one term. So this would be exactly the same equation that you saw in DFPT for computing phonons. Just in the case of phonons, the perturbation was when we displace atoms. But here, instead of moving atoms, atoms are fixed. And our external perturbation is, for example, photons or light. We radiate by electric field. We apply electric field to our system. Or it can be some other perturbation. We irradiate our sample by a beam of electrons or by neutrons. We just change perturbation. And since in our case, perturbation is time dependent or frequency dependent, so also equations has to be generalized to the frequency domain. And that's why we have everywhere omega. But apart from that, these are exactly the same equations that you saw last week. And here, let's discuss a few terms. So V prime Hartree exchange correlation is the so-called linear response potentials, linear response Hartree and exchange correlation potentials, which have this expression. We have Coulomb potential, exchange correlation kernel multiplied by the response density. So n prime is the response density. Next, this response density, it can be shown that in linear response regime, the response density is defined this way. We have factor of 2 due to the spin degeneracy, because we consider non-spin polarized materials. So we have factor of 2 due to spin. And it's defined as a product of phi prime response orbital times the ground state orbital, phi naught, plus phi naught times phi prime complex conjugated at minus omega. So notice that the response density n prime depends on phi prime and phi prime complex conjugated, but this object highlighted in yellow are actually the unknowns of the equations that we want to solve. So again, we obtain a closed loop because we want to solve these equations to find phi prime and phi prime star. But it turns out that in this expression, we have potentials that depend on density, that depend on the unknowns that we want to determine. So it's a closed loop. And in practice, we need to solve this problem self-consistently by iterations. Another comment is that in this equation, you see operators P, C with a hat. So these are the projectors on empty states. They are defined as the summation over index C, labeled for conduction bands or empty bands, projector on conduction bands manifold, phi C, phi C. And this object can be written as 1 minus projector on valence band or occupied bands. Again, you should remember that last Friday, you saw exactly the same projector with Professor Baroni. So we have the same methodology applied also in the time-dependent case. A few comments about this. So here we don't need empty states, thanks to the projector on empty states, PC. So this is very important statement and take-home message that the powerful part of this method is that we never ever need empty states to solve this problem. In the case of Dyson method, which we discussed before, we do need empty states, as I showed before, but here we greatly simplify the problem. We don't need empty states, and so this method is computationally more advanced. And second comment, the drawback of this method is that the Steinheimer equation still has to be solved for every value of the frequency omega. You see, we have omega, and we put certain value of omega, we solve it, then we put another value of omega, we solve it second time, another value of omega third time, etc. So we need to solve it multiple times, and this is still computational bottleneck of this method. And the name of this method, apologies, it's, as you see, Steinheimer method, because this equation is time-dependent Steinheimer equation. And this method is implemented in Quantum Espresso, will be the last exercise of the hands-on today. Now, let's discuss about the third method, so-called Liouville-Lanczos method. So this is really the central method of today's lecture. And this is one of the unique features of Quantum Espresso. This is not common. It was developed in 2006 by Ralph Gebauer, Stefano Baroni, and co-workers. The method was first introduced in this paper. And the idea is the following. So we start with the so-called quantum Liouville equation, which describes the evolution of the charge density matrix operator. So I would like that you take a moment to think that this is a charge density matrix operator. So notice the word matrix and notice the word operator. It's not simply a charge density, which is a function, but this is, first, it's not a function, it's a matrix. And second, this is an operator. So it's not a function of R and T. This is an operator. So this is why we write rho. And we introduce hat to remember this is operator. And it depends on time. So for this object rho with a hat of T, we write the so-called quantum Liouville equation, where on the left we have time derivative of this matrix operator rho. And on the right, we have a commutator. So this square bracket for two objects is the notation for the commutator. And we have Conchem Hamiltonian, which is also operator, depending on time. And again, rho of T, which is the matrix operator. Now we want to solve this equation. Notice that we can write the charge density matrix operator rho with a hat of T in the coordinate representation. So we write now rho of R, R prime, and T. So notice that we don't have now hat, because hat is for the operator, but now we have operator in the coordinate representation. So instead of writing a hat, we write R, R prime. We have still time. And this object, which is the charge density matrix, has this definition: factor of 2 due to spin, sum over valence band or occupied bands, and the product between phi and phi prime. But they are at different points in space. One is at R, another at R prime, but at the same moment in time t. So notice that this object depends only on occupied bands or valence bands. We don't need empty bands here. So next, again, using linear response theory or first order expansion in Taylor series to first order, we can rewrite the quantum Liouville equation this way. I don't show it here in the presentation, but it's quite easy to do that. It can be shown that the Liouville equation, quantum Liouville equation, can be written to first order this form, where on the left we have the derivative of the response charge density matrix operator, and on the right we have three terms. All of them are commutators. The first one is the commutator between the H0, which is the Hamiltonian of the unperturbed system and ground state, with the response density operator rho prime. The second term depends on the response potential, response Hartree and exchange correlation potential, evaluated with the ground state charge density matrix operator. And the last term is the commutator between the external potential and the ground state charge density matrix operator. In analogy with the second equation on this slide, its linear response counterpart, rho prime of RR prime and T, takes this form. It depends on response orbitals phi prime and phi prime complex conjugated, and the ground state orbitals phi naught and phi naught star. So now we want to solve this linearized equation. Again, this is just to recap. We write it in compact form, the linearized quantum Liouville equation in time domain for the moment. We introduce this operator L with a hat, and this is actually a super operator. Why is it called a super operator? Because this operator acts itself on operator, because rho with a hat is the response charge density matrix operator. So L is the super operator because it acts on the operator itself. And this is sum of two terms that you show you saw in the previous slide. As was discussed in the case of Dyson equation and Steinheimer equation, we do the same trick. We go from the time domain to the frequency domain. So we use Fourier transformation. And now our linearized quantum Liouville equation takes this form. So instead of t, instead of time, now we have frequency omega. So I skipped the demonstration how to obtain this equation, but this should be quite straightforward. And in this linearized equation in frequency domain, we have frequency h bar omega, which is the frequency of the photon, minus Liouville superoperator acting on the unknown, and on the right we have the commutator between the external potential and the ground state charge density matrix operator. And formally, we can write the solution of this equation simply by bringing the operator in square brackets on the left. So we bring it to the right with the -1 to the power -1. So this is just formally, we can write it like this. And finally, by having this definition, this expression for rho prime, we can write the object of interest that we want to evaluate at the end of the day, which is chi, the susceptibility chi of omega. So by definition, susceptibility is the trace of the operator A with the response density matrix operator rho with a head prime. So A is the quantum mechanical one electron Hermitian operator. It can be any operator. For example, we can take a dipole. Okay, so if we put replace A with the dipole operator, so what we will have on the left, so our susceptibility would be actually polarizability. But if you put instead of operator A some other quantum mechanical operator, it would be another observable chi. We will discuss at the end of the lecture other cases for electron angelos and for magnetic systems. Okay, now we have these beautiful equations and we want to solve them in practice somehow. And now this brings us to the Langsos method. I don't know if you heard about Langsos method or not, but this is a very powerful method to solve this problem. We define the standard batch representation. We introduce new variables called Q with the index V and P with the index V. So Q is defined as a half sum of all the variables because phi prime and phi prime complex conjugated at omega and omega minus prime, these are unknowns. So instead of having these two unknowns, we introduce another two unknowns, which are Q and P. And P is defined as the half difference between all unknowns. And then we define batches because we take a set of Qs and we label it as a bold Q because it's a set or batch, and P is a set of P variables. Now, with this definition of Q and P batches, which are called standard batch representation, now we can rewrite the linearized quantum Liouville equation and frequency domain in a matrix form using these batches, standard batches. So we see on the left matrix depending on frequency and superoperators D and K, and on the right we have this quite complicated object: projector on empty states, external perturbing potential, and ground state orbital. So what are these operators D and K? The D operator, the action of the D superoperator on the Q is nothing but ground state Hamiltonian minus occupied band's eigenvalue. And the action of the K superoperator, this is a more complicated object because it contains inside all interactions. So we have Coulomb and exchange correlation electronic interactions inside. So this is quite complicated and it takes time to get familiar with these methodologies. But this is the basics of it. And finally, to solve this matrix equation in practice, as I said, we use Lanczos recursion method algorithm. We introduce two-component Lanczos vectors, capital V, which depends on Q and P, and capital U, which depends on Q tilde and P tilde. We write down the Lanczos recursion chain, where we have these vectors V and U that we just introduced at iteration I plus 1. And to obtain this vectors at iteration I plus 1, we need to know the values of these vectors at iteration I and at iteration I minus 1. Here, beta and gamma are so-called Lanczos coefficients, and L and L transposed is the Liouvillean superoperator. So L is simply the expression over here on the left without frequencies. So if we remove h bar omega and we put 0 and 0, and off diagonal we have minus d and minus d minus 2k, this is called L, the Liouvillean matrix. And in practice, we solve this Lanczos problem by iteration, recursively. And what we do actually when we solve it, we generate a so-called three-diagonal matrix. It's very sparse matrix because many elements of the matrix are 0, and even those on the diagonal, only these elements are non-zero, beta coefficients and gamma coefficients. So this is why it's called three-diagonal. But moreover, on the diagonal, we have 0, which is even better. So once we have this matrix of size n by n, when n is the number of iterations, let's say 1,000 iterations, so we have 1,000 by 1,000. Once we have this matrix, we can finally compute the susceptibility chi in the post-processing step, which is not expensive at all, this step. And we have h bar omega times the identity matrix minus our matrix T, all this to the power minus 1, multiplied by E1 of n. So E is just a unit vector, n-dimensional vector, so 1, 0, 0, 0. So the dimensional vector is n. All elements are 0 except the first one, which is 1. And zeta of n have this complicated definition. And these objects, zeta of n, are computed on the fly. So when you solve Lanczos, you do Lanczos iterations, on the fly, you simultaneously compute also this object inexpensively. Notice that we don't need empty states in this method. As I mentioned before, because we have projector on empty states. So again, this is very powerful, no empty states. Second, this three-diagonal matrix T of n must be computed only once. It doesn't depend on the frequency. So this is a second very powerful advantage of Lanczos method, that even though you see frequency here in this equation on the top left, but in practice, actually, it's just a parameter. We don't solve this equation multiple times for each value of frequency. So frequency is actually never used when we solve Lanczos recursion. And we obtain the matrix of T, which is, it doesn't depend on frequency. The frequency enters only the very end at the post-processing step. You see h bar omega. So once we have T, which doesn't depend on frequency, now we do computation of chi for different values of frequency. But Lanczos itself does not depend on frequency. And yeah, and what I said in the third point is exactly that. this last post-processing step is absolutely inexpensive. If Lanxess takes, it's really the main computational bottleneck of this method. Let's say it can take 30 minutes computation. So the post-processing step can take just 2 to 5 seconds. It's really inexpensive. Okay, and let me mention very briefly the last method. It's the Casida-Davidson method. So this last method is used mainly to study molecular systems. So it's popular in quantum chemistry, effectively. While Dyson and Steinheimer, they used mainly in solid state physics, and Liouville-Lanxess is effective both for molecular and also extended systems. So, okay, briefly about Casida-Davidson. I write down equations that you saw already before, this resonant and anti-resonant linear response equations. We say the following: the right-hand side, which is the perturbation, because we have external perturbation potential, we set it to 0, and we can write the remainder of this equation in a matrix form. It's called Casida equations. It's from the quantum chemistry community. Maybe you're familiar. And we have this matrix equation and want to diagonalize the matrix on the left. Sorry. We want to obtain eigenvalues and eigenvectors of the matrix on the left. So we diagonalize with the Davidson method. So that's why this method is called Casida-Davidson method. And the lowest energy eigenvalues is the first excitation peaks. So this is especially a very practical method for molecules, because in molecular systems absorption spectrum, you easily compute first eigenvalues, and then when you go higher and higher in energy, the density of eigenvalues becomes higher and higher, and this method becomes computationally very expensive. But if you apply this method to extended systems, like solid state systems, in my view, this method is not really efficient, in particular for optical absorption, because in solids, the density of eigenvalues is very high. So this method is not really practical. All right. So this was the overview of 4 methods. And now let's discuss about applications of these methods, in particular optical absorption, electron energy loss, and inelastic neutron scattering. So let's start with optical absorption. So far, the external perturbing potential was not explicitly defined. It was considered as some generic external perturbation. Now we are talking about optical absorption. And in this case, the external potential is defined this way. We have minus E, where E is the electronic charge. Capital E in bold, this is the electric field vector, which depends on frequency. Scalar product with R, which is the position coordinate. So with the cartoon, you see that we have a molecule when we irradiate it with light. We have photons with energy h bar omega. So with this definition of the external potential, the object that we want to compute is the dipole, bold D, which is the dipole vector. By definition, dipole is the trace of the position operator R times the response charge density matrix operator rho hat rho prime, the one we discussed before. And in the Liouville-Lanxess method, when we discussed about Liouville equation, you remember that the expression for rho prime is the resolvent. I didn't mention it before, but this is the resolvent h bar omega minus L to the power minus 1 times the commutator of the external potential and ground state charge density matrix operator. So now in this definition, we plug in the expression for the external potential, V prime. So we put this here, and then we can define the dynamical polarizability tensor of the dipole, alpha ij. So the connection between the dipole D and the electric field capital E, so the connection is via this dynamical polarizability tensor. And the expression for alpha is obtained by using first two equations. You see that alpha of ij, where ij are just Cartesian components, x, y, and z. So it's 3 by 3 matrix. So alpha of ij is defined this way, minus E and position operator at point I, or sorry, in direction I, it's x, y, z, resolvent multiplied by commutator, and position operator J. Okay, so we have this definition, and we can evaluate this object, for example, using either Liouville-Lanczos method with the code turbo-lanczos.x, or using Cassida-Davidson with the code turbo-davidson.x. So during the hands-on, the first two exercises will be exactly computing the dynamical polarizability alpha using these two codes. So Oscar will guide you through the hands-on. Just to give you an example, with this method, Liouville-Lanczos, we can compute the absorption spectrum of the caffeine molecule, shown here. So on the y-axis, we have the polarizability that we compute. On the x-axis is the energy, if you want the photon energy. In this figure, we see the convergence of the absorption spectrum. If we do 500 Lanczos steps, we see very big spikes. This is, of course, very, it's not converged spectrum. If we increase number of iterations to 1000, so we go from red to green, we see that spikes are vanishing little by little. If we increase to 2000, they get even smaller. And at 10,000 steps, we obtain almost smooth spectrum. So this black spectrum, the converged one, can be compared to the experimental spectra of the caffeine molecule. And on the right, I show another example using Cassida-Davidson method. This method was developed about 5 years ago and applied to these molecules, pelargonine, cyanine, peonine, etc. And we show here polarizability as a function of wavelengths in nanometers for each of this molecule. And using this absorption spectrum, it's also possible to compute the corresponding color. It's shown here on the right. Another interesting application that can be done with quantum espresso is to compute absorption spectra of molecules in solutions. For example, of course, molecules exist in some solutions, like in water, for example. So to simulate this, what we can do with quantum espresso, we take our molecule, cyanine molecule in this case, about 60 atoms, and we put around molecule waters. And this system is quite large because in total you can have more than 100 molecules, maybe 200, I don't remember exactly. But this system overall is quite large, and if you want to perform a straightforward simulation, it will be very expensive. So we can do some simplification of the problem. Namely, we can replace water molecules around our molecule with some homogeneous medium. And we put the dielectric constant of this homogeneous medium of the real atomistically resolved medium. So we get out all water molecules and we put in the homogeneous dielectric. But now the question is, how do you interface your real molecule with this solvent, so-called implicit solvent? So this is quite tricky. And in this work, we used the method which is called self-consistent continuum solvation model, developed by Oliviero Andriussi, Ismaila Dabo, and Nicola Marzari about 10 years ago. And there are actually two interfaces. It's actually smooth transition, but we need to define two parameters that control the smooth transition from the molecule to the medium. So inside of this first iso surface, you can see it in some hue of green color. So inside, the dielectric constant is 1. So the molecule is sort of in vacuum. But then it smoothly goes from vacuum to the dielectric constant of the implicit solvent. And using this approach, we can compute the absorption spectrum of this molecule, not only in vacuum, but also in the presence of this solvent surrounding our molecule. So there are screening effects of the electronic transitions of the molecules. When you excite electrons of our molecule, of course, you have some effect by the environment. And here we see two calculations done at the PBE level, which is GGA, and using the hybrid functional TDDFT calculation. Comparison was done with the Gaussian code, which is, of course, very popular in quantum chemistry community, computed in vacuum and also in water. So you can see really the effect of the environment on the absorption. So you see changes in the intensity of peaks, so going from red of vacuum to green, which is with water, and also the shape and even position of peaks. And when you switch from semi-local PBE functional to hybrid functional, you see also significant changes. You see the blue shift of peaks. So you see that it's also important to use good approximation to the exchange correlation functional. So in quantum chemistry community, people don't use PBE because it doesn't give satisfactory results. And people use hybrid functionals like B3LEAP. And this can be done with quantum espresso, as you can see. If you're interested more in this solvation, in implicit solvent model, you can go to this website, quantumenviron.org. There are many, many more interesting things that you can do with this in the field of electrochemistry. Speaking of solid state systems and optical absorption in these systems, so this is the result for bulk silicon. You see the intensity of the absorption is a function of the frequency of the photon. In red dots, we see experimental absorption. Okay, if we use TDDFT at the RPA level approximation, if you remember, I mentioned during my talk about RPA, which is the random phase approximation, that we completely neglect the exchange correlation effects. So we set F exchange correlation to 0. So we see the spectrum that we obtain is absolutely not satisfactory. No, it's bad agreement with experiment. Then we can try ALDA, which is the adiabatic local density approximation that I also discussed. We have this orange spectrum, still very unsatisfactory absorption. Okay, so if we try more advanced method, we go beyond TDDFT, and we can try GW, which we didn't discuss during the school. GW still doesn't give satisfactory results, and only when you use many-body techniques like Bethe-Salpeter equation, you obtain rather good agreement with experimental spectrum. If you're interested in using GW and Bethe-Salpeter equation, you can use, for example, Yambo code or maybe Berkeley GW. But this shows you that TDDFT using local or semi-local functionals does not give satisfactory results for the optical absorption of solids. You can still use TDDFT with more advanced exchange correlation functionals, which are non-local or maybe frequency dependent. That gives much better optical absorption for solids, but the computational cost of TDDFT increases very rapidly. You're going essentially towards the many-body technique like beta-salpeter. And again, if you want to experiment with these advanced exchange correlation kernels, you can try, for example, Yambo code. And also there are some studies where people try to use hybrid functionals with TDDFT, but basic hybrids do not give satisfactory results like HSE 06 or PB0. So dielectric dependent hybrid functionals that I mentioned on Thursday, that do much better job. There are some recent works by different groups, in particular by Pasquarello and Cresse. They used dielectric dependent hybrid functionals with TDDFT, and this seems to give much better optical absorption for solids. Okay, we're 10 o'clock, maybe 10 minutes more if I can just finish.
Yeah, sure.
Very quickly. Okay, electron angular spectroscopy, very quickly. Okay, now what we do, we irradiate our sample not by photons, but by electrons. So we irradiate our sample with electron beam. Now our external perturbation is the plane wave, just because free electron can be described as a plane wave that propagates space and time. The susceptibility now is the charge density susceptibility, which describes the density-density response. We have now in this expression we saw before, instead of having position operator R and R, we have density and density operator. By computing this susceptibility, we can evaluate then the inverse dielectric function epsilon minus 1 at a specific wave vector q. Because when electron is scattered in the sample, this electron transfers its energy and momentum to the electrons of the sample. So the transfer of the momentum is denoted with the q vector. And by knowing the inverse dielectric function, we take its imaginary part, and this would correspond to the double differential cross-section, which is measured experimentally. So what we compute, we have the direct link with what is measured in experiments. So this double differential cross-section measures the angle in which electrons are scattered and which energy is in some interval in energy. And this can be computed with the turbo EELS code. We will discuss during the hands-on. Some example for silicon. If you plot this object, which is the loss function as a function of energy, you obtain the loss spectrum for silicon, and this intense peak is the plasmon. So plasmon is the collective excitation of electrons. It's a quasi-particle. We will discuss more during the hands-on. Also example for bulk diamond. This I can probably skip. We can also include relativistic effects like spin-orbit coupling when computing electron loss spectrum in bulk bismuth. Compare good agreement with experiments, but I skip this. Last example, for magnetic systems, we can also discuss when we take magnetic sample, for example, bulk iron or bulk nickel, and we radiate it by neutrons. So neutrons are also inelastically scattered. In this case, the perturbing potential has this expression where sigma is the Pauli matrix, B is the magnetic field, and this is a magneton Bohr. The susceptibility is the, magnetic susceptibility defined this way, where we have M, which is the magnetization operator. We compute the structure factor S by knowing susceptibility chi, and again compare with the double differential cross-section The code to compute this spectroscopy will be available in the next official release of Quantum Espresso. Just example of application of this code, we computed magnon dispersion in bulk iron and bulk nickel. So magnons are also collective excitations, but now of spin. So magnons are collective excitations of spin. And they're also quasi-particles. So if you compute magnon spectra, a different transferred momenta Q, and we plot the position of the peak, of the magnon peak, is a function of the transferred momentum Q. We obtained this dispersion, magnon dispersion. And here we compare this work, these orange dots, with experiments, which are this rhombi. We see good agreement for iron, but for nickel, we see that TDDFT, this work and previous works, overestimate the energy of magnons. This is because of the approximation to the exchange correlation function. Very advanced application. We applied Quantum Espresso to compute magnon spectra of the monolayer chromium triodide. So on the left, we show the magnon dispersion of the monolayer of chromium iodine 3. So the energy of the magnon is in the long high symmetry directions. This is the intensity map. And very interestingly, that experimentally, there was observed a gap at the Dirac point in the magnon dispersion. You see here, the intensity is vanished here. And again, using all advanced tools of Quantum Espresso, we used DFPT that you learned with Professor Baroni last Friday. We computed phonons for this material, and we found actually that when there is a gap in the magnon spectrum, actually this exactly same energy interval, we have phonon bands that you also know how to compute. So this seems to indicate that there is interaction between magnons and phonons. By doing some detailed investigation by developing a model Hamiltonian, we managed to show that actually there is interaction coupling between magnons and phonons. If you superimpose the phonon dispersion in blue and magnon dispersion, actually in this case it's parametrized, and we apply this model Hamiltonian, including the magnon-phonon coupling, we see that there are some splittings in the magnon dispersion. And if you do it, visualize it in 3 dimensions, and you see this red as a surface is the magnon dispersion, which is cut by phonons. So this is really, you can see that you can do really very advanced studies using all these tools available in Quantum Espresso, such as computation of phonons, and also different spectroscopies for computing magnons, plasmons, and many more. This is a brief summary. You can see it on the slides. I think in the interest of time, we can skip this and answer a few questions.
Yeah, hi, thanks, Yuri. Thanks for this very clear and great talk. There are 2 questions from the stream. I don't know if you can read it or if you want me to report it here.
Yeah, if you can please read. Maybe I can see. Yes. So TDDFT cannot describe double excitations, or this applies only to TDDFT LDA. Yes, so what I said, I meant TDDFT LDA. So, I mean, double excitations is when you system observes 2 photons, one after the other. So I'm not an expert in this field, double excitations, but I think you need to use probably more advanced functionals. But yeah, I'm not an expert in that field. And then what else?
There was just another one from the streaming, I think.
What is optical electronegativity?
Yeah.
Delta chi star. I'm not sure I understand what do you refer. Optical electronegativity. I never mentioned during my talk about electronegativity. So maybe we can clarify during the hands-on. Is it also possible to include time dependence of phonons quantum espresso? So this is a very good question. So currently, no, it's not possible. So phonons are now computed at a static level. Extension to the time domain is, I think it's complicated and not currently done. I think there are some efforts ongoing in the community, but the best would be, of course, to have phonons and magnons, for example, both described at the same level of theory, time dependent, and that would naturally allows us to describe magnon-phonon interaction fully ab initio without any model Hamiltonians. But there is still some work to do in that direction. It's quite complicated. And can we study extended systems with TDDFT with quantum espresso? It depends on the spectroscopy. If you want to study electron angular spectroscopy, yes. TDDFT with local, semi-local functionals describes pretty well plasmons. But if you are interested in optical absorptions for solids, unfortunately, TDDFT with local, semi-local functionals does not give satisfactory results. Either you need to use advanced functionals, exchange correlation kernel, or you need to use GW and beta salpeter with Yambo code. So I would rather go and use Yambo with GW and beta salpeter. Is the magnon-phonon code in mainstream of QE 6.7? It's not available in 6.7. It will be available in the next official release.
Okay, there are two questions from here, so I will let Ignacio to speak. If you mute, yes.
Thank you. Thank you for this very nice talk. So usually many-body methods like the beta salpeter equation scale very badly with K points, and they require many K points to be converged. So how does that apply to these methods? What is the requirement of K sampling for these methods to be converged?
Okay. Do you refer to which spectroscopy?
Magnons.
Magnons, okay.
Yeah.
Yeah, so there is also summation over K points. So it would be great to use symmetry to reduce number of K points. Unfortunately, at present, we have the code which does not include symmetries, so it's really expensive. Also, the limitation of the code that it's used only with norm-conserving pseudopotentials. Ultra soft and PAW are not supported. So it really has some basic features, and it's very computationally expensive. And there is still lots of improvements that has to be done. So if you are interested in playing with this code, it will be still very expensive.
Okay. And sorry if I can just ask one very most question.
Sure.
Is there any interpolation method for the dispersion as we saw for phonons?
Okay. No, we don't have anything now. It's actually an interesting point, but at present we don't have anything implemented.
Okay.
But this is a good point. Thank you.
Thank you very much.
Thank you.
Okay, there is another question from Daniel Torres. If you can unmute.
Hi, thank you for the presentation. And I have this question. Chiral molecules and crystals have the property of rotating the polarization of light. Can this effect be calculated in quantum espresso with one of the methods we saw today?
Okay. As far as I understand, no, this cannot be done at present. But this is indeed very interesting point. But I think at present this cannot be studied.
Okay. Thank you.
Thank you.
We have one more, Yuri, from Ryan Doody. You can unmute now.
Yes, thank you for the talk. I was just wondering, you introduced the external perturbation in the length gauge. Is there a way, can you implement it in different gauges, such as the velocity gauge? And is there any advantage in doing so?
Okay. I'm not very familiar with this. So concerning the advantage, unfortunately, I don't know the answer. I'm not familiar with this. Regarding the point whether we can implement it, that was the question. Can we implement it? So, well, yes. Now it's not available, but we can try to do that. Maybe if I have some better answer, I'll try to post on Slack. Apologies.
I don't know if Daniel Torres wants to ask another question, or if he's still raising the hand from earlier. Maybe you can speak.
No, sorry.
Okay, no other question. So
there is, I think, one question on YouTube.
Yes.
Is real-time TDDFT implemented within QE? So in the official distribution of Quantum Espresso, it is not available. Historically, there were different efforts for the real-time TDDFT, real-time propagation. I think there was some work by Ralph Gebauer. There is work by Davide Ceresoli. Probably those codes are somewhere around. So we can try to investigate, but in the official distribution, we don't have real-time propagation. If you are interested in real-time propagation TDDFT, you can try to use some other codes by the group of Rubio, for example. They use real-time TDDFT.
Don't know if you want to take the last from streaming. There is the last question from streaming.
Yes, yes. We can calculate. We can also calculate yields by epsilon.x. Which method is good? So that's true. With there is another code called epsilon.x, which is very simple code, but it's based on the independent particle approximation. So it doesn't take into account electronic interactions like Coulomb and exchange correlation. So if you compute with epsilon.x, you will obtain yields, but that would be like lower accuracy. It's based just on DFT wave functions and eigenvalues, so that will be very approximate. With TDDFT and turbo yields code, you can have a higher level of theory to compute yields spectra. So I would recommend to use TDDFT.
Okay, Yuri, there was one late, I don't know, Nikita, are you still here? There was one person that was raising the hand. I think
Okay.
he closed it. Ah, yeah, he comes. I think this is the last question, then we close for the break. Okay. So it's from the audience here on Zoom. Nikita Shechevlanov, you can speak now.
Okay. I'm just interested that if we apply the laser field should affect through the optical nonlinearities, and it means that you should accomplish the system with equation for description of electric field. Is the electric field equation is complemented the time dependence function theory at present implementation?
Okay, so I think no, currently not. So if you irradiate your sample with electric field, I think if I'm not wrong, you're referring to intense laser field.
Yeah, well, so, the optical nonlinearities is really affect the laser.
And you're referring to nonlinear effects, correct?
Yes, it is.
Yes, yes. So this cannot be done currently. So at the beginning of my talk, I discussed that we have linear response regime and non-linear. So what was covered today was all linear response. So indeed, if you irradiate your sample with intense laser field, you have non-linear effects. And the way to go, you need to use real-time propagation TDDFT. Again, there are some works by Angel Rubio and their code, Octopus. So if you are interested in modeling that phenomena, I would use that code. In particular, you can interpret some ultra-fast experiments, pump and probe. But with Quantum Espresso, this cannot be done currently.
Okay, thank you.
Thank you.
Okay, very good. Thanks a lot, Yuri, again. And we can now break and be back with the lab, which I think is still yours, right? So see you in a bit.
See you. Thanks.
Thank you very much.